Okay, this is the start of what is admittedly one of the more complicated subjects that we cover in introductory physics, and can't really apologize or soften that blow. Magnetism is a little strange. It's most abstract forces that we're going to be talking about this entire year, or in fact, even if you went on to further study in physics. On the other hand, it can be kind of fascinating and certainly at least rewards the study. We're going to kick off with some experimental facts, things that have been discovered over the course of the last, 50,000 years or so, but mostly in the last, say, 200, maybe 300, that tells us, at least gives us insight into this thing called magnetism. Some pieces of metal attract other pieces of metals even when they're uncharged. There's the things traditionally called lodestones, you'll see, a type of metal that attracts other type of metal. And it's named after a region in Asia Minor, I guess, a Greek region, which also gives things like magenta the color. We call these particular special types of pieces of metal are called magnets. If you take one and say put it on a piece of cork and then let it float in a bowl of water, it will orient itself. It will spin around so that one end always points northward, and if you move around, that end will keep moving northward no matter how you turn yourself. That kind of device is called a compass, which I'm sure you've heard of. The end that points north is logically called the north pole of the compass, and the other end is called the south pole. And we say that for any magnet, there'll be a north pole and a south pole. If you bring a compass near some other magnet, it will align its poles. So you can see down here, the compass will spin until it's lined up in the same direction as the magnet is oriented. The north pole of one magnet will repel the north pole of a second magnet, but will attract the south pole. Likewise, the south poles would repel. That sounds a lot like electric charge, and we'll talk about that analogy in a little bit. If you cut a magnet, you produce two new magnets. Each of them are weaker, but they each are still distinctly magnetic, and they have their own poles. So you see what ends up happening is cutting a larger magnet gives you these two smaller magnets, but they have both norths and souths. Also, as kind of a weird aside, but historically, we paint the north end red. I don't know why that is the case, but it has been true for almost all compasses. I don't think the red has anything to do with it physically. It's just a standard, but it is sort of a universal standard. Some other experimental facts. Magnets can pick up some objects, such as paper clips. Usually. Depends on what the paper clip is made of. But they'll not pick up most other objects, such as glass or copper or aluminum or plastic or most organic materials. They mostly want to pick up metals, and we'll talk about why that happens later. A magnet that's brought near an electroscope does not induce charge in it. So this is not a charged object, at least not necessarily. And if you bring a charged rod near a magnet, it could induce weak polarization because the magnet is metal, but it doesn't have any strong magnetic force on it. So putting these all together, what are the implications? One, magnetism is long-ranged. You don't have to put the magnets in contact for them to affect each other. Two, magnetism is not electricity, although we will see that they are related. Much later, we'll come back and say that they're actually connected to each other, but they're not the same thing. And you have to be careful because we often analogize north and south poles to plus and minus charges, but it's only an analogy and it breaks down sometimes. Finally, there are two types of poles, which is like charge but not the same. And then maybe the most important takeaway from all of this turns out to be all magnets are magnetic dipoles. There are no magnetic monopoles. There are no single things. There's no north without a south attached. And that ends up having some deep, deep implications. Right now, it's a fact of the universe. Later on, we'll talk about some implications as to why that's the case.